Okay, I forgot to sign in sheet, so I'm going to pass around a sheet of paper. The back of it is something we'll be going over next week, so don't even worry about it. Just please print your name because I can figure it out later. Labs, all black here. Okay. We'll go ahead and get started then. So don't freak out. With our reminder tomorrow, that's why there was no puzzles for tonight. Number two, you do have a homework due on Sunday at 11:59 p.m. I apologize for the delay in getting it posted. I did post it this morning. If you have not done the math connect puzzles associated with the degraded rate laws, they are due also this Sunday at 11:59 p.m. And then finally next Monday is exam number 2. Look at Blackboard to see what will be on the exam. I believe the only thing that's listed there that is coming off is I am not going to put reaction mechanisms on the exam. Now, as far as what you will receive when you get your exam on those back pages, like you had last time, that you removed from the exam, you will have your periodic table again. You will have a formula and constant sheet, and you will have your solubility rules. Now, formula and constant sheet, folks, I don't make it just straightforward. In other words, I don't put everything with the 0th integrated rate law together. Everything with first integrated rate law together. You got to know what you're doing. You got to know what you're looking at. I don't make you memorize every little detail, but you should be able to recognize what you're working with and when to work with what. So keep that in mind as you're progressing. Any questions? But you will have all the formulas will be on there somewhere. We've done a lot of formulas this week. The only formula I refuse to put on this test, so don't even ask, is molarity and density. If you don't know those, you don't need to be in Chem 2. You need to go back to Chem 1. But the formula for molality will be on there. The formula for mole fraction will be on there. The formula for the change in temperature for boiling point will be on there. It will all be there somewhere. But you gotta know what to do. Questions? Yes. Did I only give it one? I'll go back and give it a second attempt.
Also, one of them on there, I think, is incorrect, because it doesn't allow you the option.
You'll have to send me an email about that one, because I don't know what that one is. So. But I will go back in. No, homeworks always give 2 attempts, so I don't know why I hit the 1 attempt. I'll go back in and give it an attempt. Only on quizzes am I that tough. Or tougher. Other questions? This is what I'm getting at, folks. I'm not going to get mad if you bring up stuff. And if that problem is truly incorrect, it will come off the actual problem sheet because, and I'll report it to active so that it can get corrected. But I got to know these things so that I can do my due diligence. Okay. So what we're doing today, I'm going to start with a bunch of pictures, to be honest, because that's the easiest way to explain some of this stuff. But we're going to focus on collision theory, energy of activation diagrams, including how a catalyst alters the energy of activation. And then we're going to be working with the Arrhenius equation. The Arrhenius equation allows us to calculate the energy of activation if we know the rate constants and the temperature, or it allows us to calculate a rate constant if we know everything else. So we're going to be using the Arrhenius equation, and folks, you've actually already seen something very much like the Arrhenius equation that we will be using primarily because it's very much like the Clausius-Clapeyron equation. So that should help a little bit in because you already have mathematical skills from the Clausius-Clapeyron. So that is the plan for today. If I have time, I will start getting into reaction mechanisms. But I don't know if I'm going to have time, and that's why they are not going to be on Monday's exam. And even if I did have time to get started, I would not have time to do it properly. So, okay. So let's go into Zoomer. Okay, let's see if it'll. So collision theory. We've already actually introduced this concept, but I don't know if I've termed it collision theory. Collision theory basically says that the molecules must collide with the correct orientation for a reaction to occur. So in this particular example, you will see that we have a hydrogen going into the going into a double bond area. Looks like, even though you can't really see it. And that would be a good collision. But if you turn that molecule around, you're not going to get a reaction because that collision is not going in the correct direction. Same thing here. If you have the green molecule and it collides with one of the black atoms, if it's not coming in right at that double bond, it's not going to have a proper collision. So again, this is basically illustrating that the molecules must collide with the correct orientation for a reaction to occur. You get anything else, any other orientation, the reaction is not going to occur. Now, what can we do to get these molecules to hopefully collide frequently with correct orientation? Huh? Well, we can't hold them still.
Again, the correct orientation.
It would be very difficult to do that unless you're putting it on something.
No.
Catalysts can help. But what else can help?
More collision.
More collisions. What's going to cause more collisions? Heat's one way, higher concentration. So let's face it, if I only have a couple of molecules, they may or may not fly the correct orientation. But if you put a ton of those in there, there's a pretty good chance that they're going to collide with the correct orientation. You're going to get some collisions with correct orientation. Now, besides the orientation, you also have to have collisions with the correct energy. And what this is showing, even though it's not important, this kind of framing, is you have two different molecules. You have an orange molecule and you have a green molecule. And this molecule in this green molecule can come together and bounce, and then they're separate. Kind of like what was discussed with an ideal gas. They collide and then they go in the opposite direction. So if they don't have synergy, they're just going to collide and they're going to bounce off of each other. They have to come in with the correct energy. And only if they come in with the correct energy, you can get green and orange molecule. Only if they come in with correct energy do you have the ability for those to collide and form something. Now, we've already discussed concentration helps, but what else did we say? Temperature. And temperature is the biggest factor here because temperature provides energy. Heating a mixture up provides its energy. And if you provide it with more and more energy, then yeah, they're going to collide and they're going to have a lot more energy when they collide, so that a reaction is more likely to occur. Now the question is, how much energy is needed for these reactions to occur? And that's where an energy of activation diagram comes into play. And I'm actually going to draw it instead of using this, simply because I want to get rid of that screen. So when you have an energy of activation diagram, from a general perspective, on the x-axis, we are talking about the reaction progress. On the y-axis, you are talking about energy. Now, if we're talking about a reaction, when we look at a reaction, the reactants are on the left. So that is our starting point. Now, those reactants, we just said those reactants have to collide with the correct energy. That correct energy is dependent upon the energy of activation. If it has the correct energy to get over that barrier, then yes, we have the ability to go and form our products. Now I'm going to describe this difference between the reactants and the products in terms right now, because it's the only term we've ever really talked about in college chemistry. We're going to describe it in terms of the enthalpy, the heat of the reaction. Now you can, as we will discuss when we get to like chapter 17 to 18, we tend to discuss it in terms of Gibbs free energy, which would be accurate, actually more accurate. But as you'll find out when we get to that chapter, when we talk about Gibbs free energy, it's mostly enthalpy anyhow. Okay. Now, in this particular case, more energy is given off than was absorbed. So in this particular diagram, we are talking about a negative delta H because more energy was lost by the reaction than absorbed. And in other words, this is an example of an exothermic reaction. But not all reactions are exothermic. We also know that we can have an endothermic reaction. Even with an endothermic reaction, your reactants will be on the left. You will have an energy of activation that must be overcome in order to get to the products. That energy of activation is the distance from the reactants to the, in this particular case, if I'm going this direction in a reaction, it is the distance between the reactants and the top of the curve. And the difference between the reactants and the products is going to be related to its enthalpy. Now, in this particular case, you had to put in more energy than you got out. Because you put in more energy than you got out, this is a positive enthalpy. And so this is an endothermic process. Now, folks, just because I have been doing the reaction in a forward direction, we'll be getting into reactions that are reach a state of equilibrium. And you can have a forward process and a reverse process. You need to pay attention to the words. Because let's say I have energy. I draw, we'll go with the same one I just drew. If I say, okay, what is the energy of activation for the reverse reaction? Well, the reverse means you're starting with your products. So this would be its energy of activation. In other words, you got to pay attention. Are we going forward or are we going in the reverse? Now, I will reiterate something that was said in College Chemistry 1. As a reminder, exothermic reactions tend to be spontaneous. In other words, once they get that spark, they go. Whereas endothermic reactions are not spontaneous. Now, folks, just because we are using this word spontaneous doesn't mean it's easy. Just because we say it's going to go doesn't mean it's going to do it, so it's going to be easy. Because if we go back to my first diagram, this is a exothermic reaction, but from an energy of activation diagram standpoint, this is easy. Because it has a very long energy of activation in order for the reaction to occur. Now it's easier than it would be to go in the reverse direction, because if it were going in the reverse direction, it would have a nasty energy of activation to deal with. But it's still, I mean, this, even though it's exothermic, it doesn't mean it's easy, because it has to overcome that energy of activation. That's where a catalyst can come in. What is a catalyst, anybody? Okay, so it's a substance that lowers the energy of activation. Is there anything else we can say about a catalyst?
You're not used up in the reaction.
It's not used up in the reaction. So a catalyst enters and exits the overall reaction. Yes, I'm using this word overall on purpose. The same. It enters and exits the overall reaction and appears exactly the same. It's unchanged. Now, we can get a catalyst to do this in a variety of different ways. One, let's just take our example that I had just a moment ago, which was an exothermic process with a decent sized energy of activation as we went from reactants to products. Basically, what a catalyst would do is it would find an alternative path. That alternative path simply is going to have a lower energy of activation. Now, in this particular case, this is a one-step alternative path. Because we only have one energy of activation pump, if you will. But folks, you got to remember, all a catalyst is something that finds an alternative path. It doesn't have to say that that path occurs in one step. Now I will pull my pictures back out. Here's an example. I know it's not ideal. But you have your reactants, you have your products. This is your original energy of activation, which you can't even see the top of. In this particular case, what they did is they added a catalyst to go from the reactants to the products. But it kind of took that energy of activation and it distributed it over a multi-step process. This would be considered a two-step process. In all those two steps, the first one has the higher energy of activation. Because once you get to the second step, you have a very low energy of activation. So it lowered this thing down some. But in doing so, it had to do so where it made it over a two-path method, a two-step method instead of just one step. Questions? Now, these points along the way do have names. The top is going to be considered to be a transition. Literally, the molecule is in a transition phase as it is undergoing the reaction. And the bottom between those 2 points is called an intermediate. So you have transitions at the top and intermediate in the trough. We will be discussing those in a lot more detail when we get to reaction mechanisms too. Because this is directly related to this example here on the left, on the bottom, is going to have more than one reaction that makes up the overall reaction.
Top and bottom again, sorry.
The one on the bottom will have more than one reaction that makes up the overall reaction.
Oh, I didn't, sorry, I didn't mean.
Oh.
The
The
trough.
the trough is the intermediate.
Okay, and the top is
And the top are the transition states. Huh? Both of the tops would be a transition because if you can almost think of this intermediate. Let me see. Let me do something. I don't think I can do that. There it is. I just have to figure out that one. You can almost, basically the reason is you can almost think of these points. The reason they're called transitions is you can almost think of this as a product that is temporary. That's why it's called an intermediate. Because you go from your reactants, you go through the transition and you hit the first product. Then that product made from that first reaction then reacts to get another transition before you get to your actual products of the reaction. Because the reaction itself is just the reactants and the ultimate products. Question. So the overall reaction is where you started and where you ended. But you got a temporary, and it is temporary, intermediate that acts like a product of a first reaction that then is used in the second reaction. We'll talk about that more. Okay. So now only one thing I wanted left to describe, because I think it's on our homework and it's a very important catalyst, that almost everybody, if not everybody's heard of, is an enzyme. Enzymes are these monster protein chains that have wrapped around and done their thing, and they have this active site. And what happens is you have your substrate, the molecule you want to undergo the reaction, it enters into that active site, and that active site starts pulling that molecule apart so that the reaction can occur. And then once the products are made, I mean, this picture in the active site, so once the products are made, the products are going to be shot out of it, and you're left with the enzyme intact. So an enzyme is just our biological catalyst. It all depends upon what reaction we want, what this composition has to be. Okay, so let's get to the math. So we've been talking about this energy of activation and stuff. We've been talking about rates of reaction. Rates of reaction, energy of activation, how do they go together? Because you got to get over that hump for the reaction to occur, you know? So let's talk about our energy of activation. Now, the original equation, that is the Arrhenius equation, is that the rate constant is that the rate constant is equal to a frequency factor times the exponential of negative E sub A over RT, where E sub A is our energy of activation. R is the ideal gas constant of 8.314 joules per mole Kelvin. And T is the temperature in Kelvin. Now, when you take the natural log of everything, you get the equation of natural log of the rate constant is equal to a negative E sub A over R times 1 over T plus the natural log of the frequency factor. It's this. A little better. Now, if you have a graph, you can use that graph.
because you have y equals mx plus b. So the slope of your line is equal to a negative e sub a over r. Meaning you have a way to determine the energy of activation by graphing the natural log of the rate constant versus 1 over temperature. Now we can expand this equation that I gave you further, and we get to the equation we're actually going to be using, which the natural log of K2 over K1 is equal to negative e. Oh, yeah, it is. Negative e sub a over r times 1 over T2 minus 1 over T1. Which, folks, this should look very similar. This is our Arrhenius equation, which should remind you of the Clausius-Clapeyron equation, which was the natural log of P2 over P1 was equal to negative delta H over R times 1 over T2 minus 1 over T1. They're quite similar. So you should have the skills to perform this math. So let's do a problem. Calculate the energy of activation for a reaction that by changing the temperature of the reaction from 273 Kelvin to 300 Kelvin causes the rate constant to increase by a factor of 7. Okay, so basically what we have here is we have a T1 of 273 Kelvin and a T2 of 300 Kelvin. And we know that it changed its rate constant by an order of 7. Doesn't matter what I put in there, it's an order of 7. And we were asked to determine the E sub A. And we know that R is 8.314 joules per mole Kelvin. So our natural log of K2 over K1 is going to equal a negative E sub A over 8.314 joules per mole Kelvin times 1 over T2, 300 Kelvin, minus 1 over T1 of 273 Kelvin. So we get 1.946 is equal to a negative E sub A over 8.314 joules per mole Kelvin times negative 3.297. In other words, all I did was kind of start simplifying things. Negative E sub A over 8.314 joules per mole Kelvin is going to be equal to a negative 0.590. So E sub A and the Kelvin actually has already canceled out. The E sub A is equal to 4.91, and that would be in joules per mole. Double checking on my math. Oh, I'm glad I did.
Okay.
I was like, I
What's
don't
going on?
negative 3 over 9100, and I'm like, where did you get 3.92 or 977 from?
That's why I always, it's hard to type and talk and write. So it's easier for me if I do it and then I go back and check it. So I always check my math because I know I'm horrible at mistakes. Let's go with 49,000. 100 joule, or in other words, E sub A could be equal to 49.1 kilojoules. And I did the same mistake a lot of students, I've seen a lot of students do, I forgot my time scale. Because it was there. Any questions? Let's look at another. Well, it's about time for our break. So instead of starting the question, we're taking a break and then we're gonna come back and do more questions. So you get a break for about 4 or 5 minutes today.
That's
Yes.
sitting there like.
That will work.
But I am just kind of ready for the rock and box.
I can email them and. Too much on what I have planned. Estimating.
That's fine. I think.
Yeah, I don't know. That's the only problem. I don't know.
That is fine. I'll email.
Because I have to ask GMT if I can, it shouldn't be a problem because I only think 2 guys sign up, so I can start posting that one.
Well, I'll email you remind, or to remind you. Thank you.
Yeah.
This.
I'll let you know. Yeah. Hey.
Hey, Charles. Let's come up with one right here.
Yeah.
That's really cool. Question. And the name was graph, and the slope of the line is today at 1.9398 times 64 Kelvin. What is the rate constant at 30 degrees Celsius? If the rate constant at 20 degrees Celsius is 1.49 times 10 to the minus 3. And the units there. Is per molar second. Want to give you a few minutes to work on it, and then I'll come in and. I don't. Could make that big of a difference.
It's. Yeah. Maybe.
I'm trying to get through the math in my head.
No, because it's using the same plate for the test year. Yes. So then. All right.
No. Yeah, I guess. That's yeah. Yes, yeah. Yeah.
Oh, I messed that up. Wow.
Yeah.
I was working with math real quick, sorry. Well, I can think it through.
The final answer real quick, how they debate.
This level along command grenade 1.9398 Kelvin. What is the rate constant at 30 degrees Celsius? If hold on, there's an error. See, even I can see errors, but I'm doing it through math.
Oh, okay. So it's still spicy.
Yeah.
That's what I got, and I was like, I was a negative rational. Okay, so again, it helped me to talk through it. Folks, I don't take my math when I'm doing it, and it's hard to do when I do it here, and I'm not paying attention. So basically, I knew that I was going to be dealing with rate constant at 30, rate constant at 40. That told me I needed this previous equation.
So natural log, I chose, it wouldn't have mattered if you chose this K1 and K2. As long as you kept the appropriate pieces together.
Getting the 2.045 there.
All of this multiplied by a positive 1.93 to 898 times 10 to the 4, which is amazing.
Yeah, no, I get 0.011.
That's what I get by the end. I get 2.045 still. So we highlighted these because I started, and folks, you can bring highlights. But I highlighted these so that I kept things together. So you had the rate constant at 30, well, that was the one I wanted to figure out, because K2 I made as the rate constant I wanted, which meant T2 had to be at the 30, so that was 303. The other one was at 40, which was 313, and it would have been 1.49 times 10 to the minus 3. Where I originally made my mistake was I put a negative here instead of a positive in front of the 4. But if you do 1/303 minus 1/313 and multiply that by the positive 1.9398 times 10 to the positive 4, you get 2.045. To get rid of the natural log on the left-hand side, you take the exponential. So you get exponential of 2.045 is equal to K2 over the 1.49 times 10 to the minus 3. And then e to the negative, or e to the 2.045 is 7.69. Is equal to K2 over 1.49 times 10 to the minus 3. And so I got, when I multiplied the 7.69 by the 1.49 times 10 to the minus 3, I got 0.0115 for an answer. Questions? Always check your work. Always check what you did in the calculator. Especially when you start dealing with complex problems. Which is what this to me is.
So I'm a little confused here. Okay, so like I figured out what I did wrong, but I got the answer just by taking that one side. And instead of doing negative 1.9398, I did that on and that gave me the correct overall answer.
Yes, because times 10 you can do E. Or no, you can't do X, you're talking exponential. You did it exponentially or the other E?
I don't know. The small one, yeah. I did the small one.
Well, you should,
Chris is putting in the small E there, it's giving me the overall.
I would not have expected the little E there to give you the overall answer. I'm not certain how that occurred.
I don't.
Luck. What now?
It's brand new that quick.
It's not a possibility. But the big thing is yeah, that's why I'm asking what G, because when I do times 10, I use the second E, and it's the capital E.
Okay, so I was like,
That gives me my times 10.
okay, I was using the wrong one, that's why.
But how you got it with the exponential, I'm not sure. I don't know. Questions?
How do you recommend studying the math portions of the test? I've never been good at studying for math.
Okay, how do I recommend studying for math? Part of it is repetition. There are some problems, I can't remember if I've got plenty up there for optional homework or not. If not, I'll post some tomorrow when I have a chance to look. But doing optional homework, and it's literally the math, for me, it's always been repetition. Is the only way to make sure that I am focusing on the math. And by me going through it, if I don't have a homework up there, I'll have to create one, which means I'll have to do the answer key too. And I'll double check my math, because obviously it's easy to get lost. But I usually do my math problems twice before I get to the final answer.
And piggyback on that, in the book, they have a lot of practice problems that you can do at the end of the chapter. And they have the answers in the back. If you don't have the book, you can find the library.
But yeah, just literally, unfortunately, the math is hard. There is no secret. Hold on, I can't hear.
Problems you're talking about, stuffy and positive or?
No, there's the optional homework. I gotta look and see if I have any of the ingredients problems. I can't remember. I've had done this. I haven't taught this for 2 years. So I gotta look and see if I've done it, got any of those in there, but it'll be. If not, I'll post it tomorrow. Any other questions? Yeah, I'm cutting out early today. See you later. And if you've got questions, your calculator and I'll see if I can figure it out. Oh, yeah. When you look back at the original ingredients equation, E sub A over R is equal to 1.
Okay, yes. Okay, also, because it's not hard there, like the game I had to take.
Right.
Right.
Right. It did, in this case.
Okay, very good.
Yeah, I'm not getting you, so. What my
Yeah, maybe amounts available.
And.
So.
Hold on, and something. Compartmentalized. They have a huge. Okay.
Instead of paying for.
Okay. Well, it's not possible.
Oh, it is not.
It's equal to what, that's what you're searching. E sub A over R was what I was talking about for the slope. Both of it together.
The other silver piece of a
Yeah. Yes. And your best place to find parking is off of Oak Street, there's a bank, and they're usually, they got a little bit of a lot, but usually it's on the street.
Is it a science?
And if you want to leave at 4:30, you drive.
Is it a science meeting?
It is a housing seller.
Oh.
So what's that? Or do you want to
Yeah.
So what do we do? Because they. And I mean, it really. Over and over, and I was trying to find where I can get the autograph. So this work, yes. But they're slow. They're slow 1.0003 and mine is like 0.00. But I can show you my graphs compared to their graphs,
I took out a lot more problems because they only took a couple out and I took any multiple stuff out. And then there were some that we had jumped back and forth. I had 6 hours on graphs.
Oh, I believe that.
Because I wanted it to be a straight line and my slopes were way different. I have, like, I have. How should I was, can I have the graphs, to and I'm uncomfortable with the answers that we did. And I know they're young or whatever, but I think they're great. But I don't want my grades to reflect. So anyway, like, not that they're lazy. So it makes sense, like,
What on that should be done. I mean, it's number one, it's the next class is will be in. We've got one more rival we use this class. But one thing that should probably be done is for everybody wins. The graphs. That is one thing that should be done.
Alright,
No, you're fine. I made sure, I filled out my own data, because even the first time that we were in the same group,
Right.
I asked for the data and they, no, I wasn't given it either. And so when we split, the way we did it the first time is that, okay, I'll take these two answers, you take these two answers, and you take these two answers, and we'll all come together. But the ones that I took, I needed some of the data, and I didn't do those parts in the questions. So I was like, I can't really knowingly answer this question, if I don't have this data. And I was given it, so I had to really like ask other people, like Jake from a different lab, what to do. So
So I have a multitude of options here. Number one is before you go to park. You should write.
Yeah.
Or anything that, you know, is going to be. You could finish up the line, and you gotta get finished, but that's usually a start for a while.
Yeah.
But the other thing I would suggest is in the next life, find a different group. Because you're not married to that group, you can,
Right.
you can move around. And
there's nothing wrong with it.
but it doesn't make a difference to the one, let's consider that. I think it's the best make a difference in the older and the younger. And it's not necessarily that they're, you know, anything to do with it.
Yeah.
It's a matter of just the way persons work.
Right.
You can be a great person and not, I mean, my color roommate, my first roommate, I did not get along with
Right.
until after I was no longer the roommate.
Yeah.
So
That's-
it's a matter of you can be friends. But just the way you think about coursework is different.
Yeah.
Think about it.
I was frustrated. I was gonna come see you today, but I had a huge exam and I just studied my butt off for it earlier today. And I missed your office hours to look up and think, oh my God, it's
So
so
we're
hard.
not even knowing when I was there.
I was going to ask if I could just print out my different data. And, but if it's like so far off and I'm like, you know what, I think that's wrong. And like when,
You don't have to put in the same thing. I like it.
cause it's, I don't know, it's easier, yeah.
Priority, but anybody, I mean, there was another group of 5 people. 2 of them stayed behind last week to work on everything, the other 3 left, as soon as all the data was gathered. And I told them to turn in something stop. Because I didn't, you know, they had the advantage of that being able to ask questions.
Yeah, I feel like part of it is partially my fault because I would not take. I don't wanna sound pretentious, but as an older mind, I get things much faster than some people. And, when it came to the rate law, they kept saying that the rate law would change, and I was like, no, it doesn't change, the law itself doesn't change, the constants in them can change, their concentration can change, but the formula that you use to find everything is the same no matter what. And they could not see that, and I pushed it hard because I was uncomfortable with the graphs, I was definitely not taking 2 hits.
Sorry.
And I think that's part of the reason they wouldn't give me the data. but again, I don't know.
I don't think.
Yeah,
Personally,
I'm definitely gonna sit for a while.
just move on.
Okay,
Or, I mean, you know, some people in the lab, you can say, hey, you can wait until they look at it.
Yeah.
And walk in with her as they do this. Partner.
Okay.
That far right hand corner has three industry members in it that are. Being very take their time.
yeah,
You know, it's all dependent on personalities and not everybody knows.
Yeah.
It's okay.
Okay.
And you just say, hey, I'm just moving around.
yeah, I still like them, I just don't necessarily want to work with them in the future, because I feel like. I think the graphing lab, I did really well on, I'm probably sure, but the last two labs, I have been like losing sleep over. I'm like, I'm that person that's like, okay,
Just email to me or Curtis.
okay. I mean, I won't this time, but.
Well, I don't want your grade to take a hit if you're not confident. I mean, it's. Y'all are doing me a favor by allowing it to be, turned in separately, and I'm gonna have to edit. That's okay, I'll edit. this.
Oh, so that no one can hear our conversation.